We scan across all wavelengths to determine the lambda max. The lambda max is the wavelength at which the solution absorbs the most light. This is the wavelength of light most likely to produce results across all solutions regardless of concentration. If a scientist chooses a wavelength at which the solution being tested absorbs little or no light, they may calculate an absorbance of 0 for all samples. However, if a scientist did not choose one wavelength to test after scanning across all wavelengths, their data would be inconsistent and would not show a linear correlation. We then scan all samples using one wavelength because we want to obtain consistent data to construct a calibration curve from which the concentration of an unknown solution can be calculated.
The Beer-Lambert law, or Beer's law, is the linear relationship between absorbance and concentration of an absorbing species. The general Beer-Lambert law is usually written as absorbance equals epsilon times L times C plus B. A represents absorbance, which was determined with the spectrophotometer. Epsilon represents the wavelength, or lambda max, derived from the graphs generated by the spectrophotometer. B represents the y-intercept, which should be 0. L is a path length that the light travels. In this case, the light traveled 1 centimeter, or width of the cuvette, so L equals 1. C is the concentration of the solution. This was determined mathematically using our data and the other variables in the Beer-Lambert law.
The relationship between absorbance and concentration is a linear positive relationship as expressed in the Beer-Lambert law. However, if the spectrophotometer were not zeroed before each series of trials, concentration could not accurately be determined from absorbance. If the spectrophotometer was not zeroed, B would not equal 0. In other words, the data would show that a solution with a concentration of 0 absorbed light, which would shift the absorbance by the value of B.
Start adding all of your solutions into the cuvettes. Make sure that you fill up to the line but not over the line. Fill up with stock solution, all of your dilutions, and your blank solution.
Check, yes, Juliet, are you with me? Rain is falling down on the sidewalk. I won't go until you come outside. Check, yes, Juliet, kill the limbo. I'll keep tossing rocks at your window. There's no turning back for us tonight.
Be sure to clean your cuvette before putting it into the spectrophotometer. First, you're going to put a blank in so that you can zero the solution.
Lace up your shoes. Here's how we do.
Once you've zeroed, put in your stock solution. Make sure to clean both sides and put it in very carefully. Boop-a-doo. Ta-da! Then you're going to scan across all wavelengths.
Run, baby, run. Don't ever look back.
When you scan across all wavelengths, you're going to find a lambda max. For us, that was about 607 nanometers. Switch to the program that scans against one wavelength and put the cuvettes inside, cleaning them off as you did before. Put the blank in first so that you can zero it. Once you're done zeroing, put in the stock solution.
They'll tear us apart if you give them the chance. Don't sell your
Make sure you record your data.
cards. Don't say we're not meant to be. Run, baby, run. Forever we'll be you and me. Check, yes, Juliet, I'll be waiting, wishing, wanting yours for the taking. Just sneak out and don't tell a soul goodbye. Check, yes, Juliet, here's the countdown. 3, 2, 1, now fall in my arms. Now they can change the locks, don't let them change your mind. Lace up your shoes. Here's how we do. Run, baby, run. Don't ever look back.
Be sure to clean up your station when you're done. That way you don't end up like the dinosaurs from the last video.